Hello and welcome everybody. Thank you so much for tuning in for this installment of the Dupont Water Solutions Water Academy. Today's webinar is the second in our closed circuit reverse osmosis series, and we'll focus on designing CCRO systems using the WAVE modeling software. My name's Kevin Clark, and I'll be your host today. Our speakers for this session are Brent Stewart and Garth Parker. As usual, before we get rolling, let's take a moment for some general housekeeping. You can access all the engagement resources from the bottom of the screen simply by clicking on the colored icons. You can resize and move the panels around as you wish to best fit your screen. We would appreciate to hear from you, and the best way to raise your questions or comments is through the Q&A box, which you can launch via the purple icon. If your question is longer or you'd like a more personal response afterwards, you can send an email to our speakers by way of the Meet the Speakers icon. And to earn a printable course certificate, you just need to attend the first 30 minutes of this webinar. If you're able to hear the audio, but having trouble seeing the slides advance, there are a couple quick fixes. You can refresh the player console by pressing F5 on your keyboard or Open Apple R on Mac. And generally speaking, it helps to shut down any other programs that are running in the background, which might limit your bandwidth. If none of the above works, please request help from our webinar producer, Inga, through the purple Q&A box. Now back to our topic, and I'm happy to introduce our speakers. Garth Parker is a research scientist at Dupont Water Solutions and has been the technical leader of the WAVE development team since the project's inception. Garth has a PhD in chemical physics from the California Institute of Technology and is based in Philadelphia. Joining Garth today is Brent Stewart. Brent is a Canadian engineer with over 15 years of experience in reverse osmosis. His primary role is application sales support for CCRO technology, and he's been the technology lead for the CCRO integration into WAVE. Brent earned his environmental engineering degree from Dalhousie University in Halifax. He has an MBA from the Polytechnic University of Puerto Rico and is joining us today from Boston. We've put together the following agenda for closed circuit reverse osmosis. The second class in this series will focus on a WAVE software introduction and is intended to equip participants with the skills to be able to design an appropriate CCRO solution for both water and wastewater applications. Future classes will be industry-specific, using actual case studies that will highlight the value that CCRO brings to specific applications within a market vertical. Today's agenda is a deep dive into the WAVE software. We're going to present an overview of CCRO technology, an overview of the new CCRO icon in WAVE, and an overview of how to produce CCRO designs and how they differ from traditional RO. And we'll run through 4 cases in order to demonstrate this. So to kick things off for this session, it's over to Brent for a quick primer before we dig into WAVE.
Thanks, Kevin. Hello, everyone. Excited to be here. I'm just going to go ahead and share my screen. So it should be up now. So the goal of the next slides is to spend about 15 minutes to provide a better understanding of CCRO technology in the context of designing and running projection. So let's jump in. CCRO, a semi-batch process that is always one stage, replacing stages with cycles. Feed equals permeate during what we call closed circuit. We concentrate up the TDS, and then we flush to drain in what we call PF mode. And we do that before the supersaturated salts have time to scale up the membranes. CCRO is super easy to both design and operate, but not intuitive to people familiar with traditional RO. One way to wrap your head around it is to think of it like a UF system, where feed equals filtrate, you build up the TSS, and then you backwash every 10 to 20 minutes. flushing out the total suspended solids. The recovery is therefore a function of the backwash frequency. Same or similar with CCRO, feed equals permeate, TDS builds up, and then it's flushed to drain every 10 to 20 minutes. The recovery being a function of the flushing frequency. CCRO technology is not a steady state process, meaning we have varying flow rates. Let's have a look at the two modes of operation, CC and PF. Again, during CC, feed equals permeate. Typical duration is 10 to 20 minutes. The pressure builds up as the TDS is concentrated. The high pressure pump is on a PID loop with the flow meter and VFD, allowing for constant permeate flow or flux. After hitting the target recovery rate, concentrated brine is then flushed to drain in the PF mode, and that duration is roughly 1 to 2 minutes. During PF, we typically increase the flow by 120%. So that's an input in the wave flow calculator. And then we decrease the permeate because significantly because the circulation pump is off. And then the cross flow or concentrate flow rate per pressure vessel works out to be about the same. So in this case, you can see they're both 100. If you run at 90% recovery, you'll spend about 90% of your time in CC mode. So let's have a closer look. Note we have 3 different recovery terms: system, CC, and PF recovery. So the system or average recovery is a function of how often you flush. The PF recovery is the same as traditional. So in that last slide, it was about 17%. And lastly, we have the CC or cycle recovery. Let's take an example at 50% cycle recovery. 100 feed, 100 permeate. 50% recovery means half goes to permeate, half goes through the circulation pump. So it makes for easy math. Now, if you wanted to lower the recovery, increase the circulation pump flow rate, say from 100 to 200, the total membrane feed would therefore be 300, and 33% of that is your 100. An important note or difference from Rosa is we previously inputted the cycle recovery. Now we enter the actual flow rate per PV. One way to visualize or compare traditional and CCRO is the following diagram. CCRO replaces stages with cycles, always one stage, but if you stretch it out, you can think of it like this 4-stage system shown. Constant feed and permeate during CC, concentrate up the TDS at about 50% recovery per stage, and then we flush to drain. You can think of the circulation pump as an interstage booster, except for on every stage. That's a big advantage. The high pressure pump provides the other half of the water to the next stage, which brings me to the slide text. CCRO is not simply a concentrate recycle, excuse me, just the opposite. Same as traditional, sending 100% of the brine to the next stage or cycle, except CCRO dilutes the brine with raw feed water, decreasing TDS versus increasing, which is why we have so many more cycles than a 3-stage traditional RO. The CCRO process dramatically simplifies both design and subsequent operation. The main reason is CCRO uncouples recovery, flux, and crossflow. Unlike traditional, they may be manipulated separately. The high pressure pump sets your permeate rate or flux, since CC feed equals permeate. Average recovery is a function of time, and crossflow is set by the circulation pump. A good way to demonstrate how easy CCRO is to take two common design warnings: not enough cross-flow and element recovery too high, or over-flexing the lead element. Looking at the first warning, you see a limit of 20 or 4.5 cubes an hour and a value of 12. To get rid of that warning, you literally enter 20 or higher into the wave CCRO flow calculator. Now compare that to traditional. Try and get the same cross-flow or higher. Inevitably, it turns into this hydraulic balancing act of stages, permeate throttling, an interstage booster, and concentrate recycle. And what happens to traditional on wastewater reuse projects with large feed variation? CCRO, on the other hand, is the same design at 75 or 98% recovery. And before we go to the next slide, regarding the second warning, the element recovery too high, so increasing the crossflow decreases the cycle recovery, which in turn is decreasing the element recovery. Now let's have a look at a few screenshots of wave. The screenshot we're showing is the same configuration tab, so CCRO and gold on the left, and then traditional and green on the right. They're the same, except CCRO is much simpler, since it's always this one-stage system, one-stage design. So no interstage permeate throttling, no interstage booster, and no concentrate recirculation. What's new and what's different is the flow calculator, and we'll spend a little extra time running through this. The flow calculator is neatly organized into average, PF, and CC mode. So if you take the permeate flow, for example, 100 would be the same as traditional, that's the average flow. And then during PF, we decrease it. And then during CC, we increase the flow to make up for the lack of permeate during PF. So there's 5 main inputs here. Most of the time, you're going to accept these defaults, with the exception of inputting the recovery rate. Look at the PF cycle. So we have 2 levers, the feed ratio and the recovery. And then for CC, you input the concentrate recycle, which was previously a percentage input, as I mentioned, but now you're entering the actual flow rate per pressure vessel. So for those that prefer the percentage approach, the rule of thumb is 10% per membrane. So 5 elements in series gives you that 50%. And you can see on the flow calculator, the 20 GPM per V roughly gives you that 50% recovery. And lastly, we have the pressure vessel size, which is simply the length of the PV. The default is to have 1 spacer or blank. So if you have 5 elements in series, the pressure vessel would default to 6. And that spacer increases the volume, which increases the CC duration, which we typically want for flexibility to run at lower recoveries. And when I say lower recoveries, I mean 75 to 80%. The second last screenshot, RO design warnings. So it's a good time to highlight we're following the same design guidelines as traditional RO. It just got easier to avoid and get rid of the warnings with CCRO technology. We walked through the first 2 rows. You can see the recommendation in the right column. Generally, increasing crossflow is always going to help. The next warning is cycle 1, meaning PF mode. So there we'd increase the feed ratio and decrease the PF recovery. The next warning is the same, but it's the last cycle. It's not the first cycle, so we know it's CC mode. There we simply enter a higher cross flow rate. And the rest of the warnings are actually CCRO design guidelines. You can see that they're in general and not tied to a cycle or element. So if you look in that box, you see that there's no number. So I want to stress, these are secondary to element warnings. simply guidelines to avoid the warnings in the first place. There's a couple of exceptions to above, one being CC duration should be greater than 5 minutes. And you can do that by adding volume, decrease the flux, extend the pressure vessel, or add spacers. Wanted to demonstrate just quickly constant feed flow or permeate. So regarding constant feed, maybe you have a carbon tower upstream and you need to hit your empty bed contact time, meaning you do not want to increase the flow during PF at 120%. At higher recovery, we're using less water, less feed water, so it's rarely an issue. Nonetheless, you can do this by simply setting the feed ratio at 100% instead of the default of 120. And then there you can see you have a constant flow rate. The last point is constant permeate, if required. Typically not going to a product tank or mixed bed. Nonetheless, if you double the flow during PF and then increase the PF recovery to the same rate as CC, so now you have the same recovery and the same feed rate, you end up with the same permeate flow rate. So before we jump into the live wave demo, Dupont has two products, Reflex for high recovery and low pressure, and Reflex Max for low recovery, high pressure, just the opposite. We cannot currently model the latter in wave, so you're limited to that 600 PSI or 41 bar. Please contact Dupont for assistance outside these ranges. And that's it for the slides. So let's jump into wave, and Gareth will share his screen.
Hello, everybody. Should have be sharing and showing wave right now. So our first example, as you sort of got from Brent's introduction, CCRO is designed very similarly to a standard wave RO design. We have a new icon. It's this gold CCRO icon. So we will drag over our gold CCRO icon, and we'll set the flow rate for our first design. And
so maybe 23, 25, that works.
Yeah, then we'll grab from our water library. We'll just grab a water. So we're sort of assuming that you are an expert in wave by now, so we won't spend too much time on the basics of using wave. So we go over to our CCRO screen. We will choose an element. We'll take a look at our flow calculator. And as Brent mentioned, you have your recovery, feed ratio, and recovery for the PF cycle, the recycle rate for the CC cycles, and their pressure length. And these are essentially the 5 variables that you would play with on the flow calculator page. And probably 90 some odd % of the time, you can just accept the defaults. Over here on the main page, you're going to want to adjust the number of pressure vessels to give a reasonable flux. We don't want to be at 121. We want to be, somewhere down around 100 and, about 20 thereabouts. So we'll pick 5. That should be fine. And at this point, you would just,
Yeah, I was just going to say that's really it. It's really that easy. So yeah, we can open the summary report and just have a quick look, and then the next case we'll dive into the details.
So, and you got your summary report. It will look very similar to the RO summary report. The big difference is we have gold headings instead of green headings, but 90 some odd % of the report will look the same as what you're used to. So that's really, in a nutshell, just how easy it is to design a system in Wave with the CCRO icon. So Brent, okay. I know you had a more detailed example you'd like to run.
Yeah, let's just run through another quick one here in US units. So maybe
Sure.
essentially the same example. Let's go with 100 GPM.
100 GPM. Feed, bring in the CCRO icon. Feed water, grab a feed water. And now we can go over to our CCRO page again. Okay.
Yeah. Yeah, so we'll adjust pick a membrane and adjust our
pick a
flux
membrane.
rate.
Yeah, so I guess the first thing to note is we have 5 membranes that are specially designed for the CCRO process. And they're the SOAR 3000, 4000, 5000, 6000, 7000. They're in order of increasing rejection. So 3000's the loosest, 7000's the tightest. Normally, a good place to start is the 5000. It's a good default place to start, and then you can look at your product quality and go up or down in rejection if you need a higher quality water. Check the flow calculator.
A comment on the membrane. So there'll be literature to follow on the SOAR elements.
Yep. Okay. So we've come back to the flow calculator, and I think, Brent, you wanted to use all the defaults here, correct?
Yeah, let's just go with the defaults again.
Okay. Everything's nicely populated.
Let's set the flux rate, so maybe 4 or 5 pressure vessels.
Let's see. 5 enough for you?
That works. Yeah, so this page is essentially the same. We'll just highlight one new feature here. So the advanced properties. Can you pull up that window, guys?
Sure. So here's this the one new feature on this page is the advanced properties window. There are 3 inputs on this page. The first 2 have to do with sort of the scale of the system and size of piping and things, which get into the volume and the recirculation loop. And until you get down to the detailed piping volumes, you can just accept the defaults for the first couple of items. The last thing is in the report, we actually have a table where we sort of highlight the water savings and what's that's worth over time against a traditional system. So for that, what we do is we just gave you an option here to say that your traditional RO system, you could probably get up to about 75% recovery. So if you wanted to, so the WAVE report will compare our 90% CCRO design against a 75% traditional RO design. And if you wanted to change that traditional design, you just change this number right here. Okay.
Great. And if we wanted to change the cost of water, how do we do that?
Sure. Since one of the selling points is obviously you get much higher recovery, you save on the cost of water. You want to make sure you have an accurate cost of water. So you would go up to user settings. And if you come over to the operating cost page tab, there's a place where you can enter your cost for raw water and wastewater. And these are obviously would be highly dependent on where you are in the world. So for your example, Brent.
Yeah, let's go 6 and 8. Those are common muni prices here in the States.
Okay. And then you hit save and close, and those are now the values for this particular project. So now let's just go run the report, and then we can dig into it a little further. Okay. The top table in the report, just sort of a hydraulic overview, is the same as in standard RO. And the RO system overview table is pretty much the same as what you see in the standard RO. Then we have the 2 new tables. We have the CCRO overview table. And this is essentially a summary of a lot of the inputs from the flow calculator that are unique to CCROs. So the number of elements plus the length of the pressure vessel. As Brent mentioned, you like to have a spacer in there just to get enough volume for the concentrate loop. The recovery for the different cycles, the feed ratio, the different concentrate flows, and the length of each of the different types of cycles. And so this one says we'll do a complete cycle in 8.5 minutes. So we'll spend 1 minute or just under a minute in the PF and 7.5 minutes recycling the concentrate before the brine dump. And then next table shows the
sustainability. Yep.
There's a little sustainability table which just shows running at 100% of the time, at 90% recovery. This is what my concentrate volume is. At 75% recovery, this is what your concentrate volume would be. So you get the savings in water, and you can turn that into $1 per year number. The rest of the report is essentially identical to what's in the standard RO report. The one thing we did is, Brent mentioned, instead of thinking of stages, we think of cycles. So what we tabulate in most cases will be the PF cycle and then the first and the last of all the CC cycles. Essentially, if the hydraulics are good for the first and last CC cycle, then they're going to be good for every cycle in between. So we'll show 3 rows or 3 cycles. In most of the places where an RO report would show you stages. But you get your water quality and design warnings, none. And then here's the element by element, what's happening at the different cycles. Okay, anything else you'd like to point out, Brent?
No, that's really it. So you just have this theme of replacing stages with cycles, so that the report really does look the same. The only thing I would highlight is on the sustainability report. So the annual savings, just going from 75 to 90% recovery, was $110,000. So, anytime the customer is paying for water to the municipality, there's just tremendous opportunity to save money and not waste water. Mm-hmm. Okay, for the next case, we wanted to show a double pass, so we could take the same example and just add a second pass. Sure. How would we do that?
Okay, so to add a pass, just like you would for normal RO, there's a button here called Add Pass. We've added a second pass. We have, once again, it's going to have 1 stage in it. Because we're running at such high recoveries you can actually run both passes at about essentially the exact same physical layout. So we ran 5 pressure vessels in pass 1. We'll run 5 pressure vessels in pass 2.
Yeah, and then normally most people would increase the pH to 8.3, yep. 8.4.
Sure. Okay. So the pH adjustment, do up here, you can do an add chemical degas. And this is where you could adjust the pH between stages, which would help with getting rid of any residual CO2 that passed through the first pass, and other weak acids like silica and boric acid. Okay, so we have our caustic addition to raise the pH. We'll just double check the flow calculator. And because you can recycle all of the concentrate from pass 2 back to pass 1, you can run your system at a very high recovery. So if I run both passes at 90, I'm still going to end up at 89% for the system. So the second pass did not cost me much in the way of water. Okay, I think everything looks okay. So we'll just run the report.
So the report again is essentially the same. It's just duplicating the information. While we wait for that, the one thing I would highlight, so CCRO, it's the same design at 75 or 90% recovery. So it gives you the flexibility to have, you could have identical systems for the first and second pass. If you didn't want or need that flexibility, then for the second pass, we'd typically fill the pressure vessel. So 6 elements in a 6-element long pressure vessel, or 7 and 7.
Okay. So just showing that the report is in fact very similar to what you saw before. Now we've added the column for the second pass. Sustainability. And the one other thing we were going to show is if we go to the detailed report.
Yeah, we forgot that. The electricity table? Or?
Yeah.
Yeah.
So all the way at the end of the detailed report, and let's blow this up. We have a table that's, well, we're talking about how much electricity we use, but we also get a little more detail about all the different pumps involved. So you can see that your main feed pump in PF mode's at 129 GPM. In boost mode, it's at 107.6 GPM. You can see what your pressures are going to be. The boost was 47, and then during the CC, it went from 188 to 204 as it concentrates up. And then you have your recirculation pump, which is, for this particular design, was 100 GPM. But that's running at a very low pressure, only 9.6 PSI, because that's essentially just offsetting the pressure drop through the modules in the main pressure vessel. So you can actually see a nice little summary table of what your pump capabilities are going to be. So looking up your pump curves.
Yeah, it's a great summary. I would note that the same information is in your flow table, but this is just a cleaner presentation. All right, I think it's
a couple questions from the audience, if we could.
Sure.
In this 2-pass design, is there a tank required in between?
Yeah, so we have, a lot of times we'll put a CIP tank in between, so it doesn't add any tankage, but we do have the flexibility to go direct.
Yeah, we would have to go back to the flow calculator, and as Brent showed, you could adjust the recoveries for the PF cycle to get a constant flow through everything. This was assuming a little tank, just to balance out the flows. And
can you show how you might change the number of elements in the design?
Sure.
Sure. Go back. Why don't we could pull up the next case, and then we can show that.
Okay.
We're gonna go into a more complicated, challenging application. And this is the last case, so feel free to ask questions, because we'll just leave this up, and we can use this example, the last case, to answer any question.
Okay.
Yeah. So for this one, we were going to go in SI 170 feed cubes an hour.
Okay.
And then you had it.
Very complex water.
Yeah, so this is a refinery reuse, 3000 TDS, running at a pH of 10.5 to convert the organic acids to soluble salts.
Okay. So, okay, we have the SOAR 5000. Our LMH is too high, so we're going to need to bring that down.
Yeah, let's go 50. We'll go with the lower LMH, 17 LMH, roughly 10 GFD for reuse project.
Okay.
And then we'll default to the 5 elements. So I guess we can answer that question if we go back.
Sure. Yeah.
So we have it defaults to the 5 elements, but yeah, it's the same as traditional. You can go 1 through 8 now, I believe.
Mm-hmm. So notice I put in 4, and my default pressure vessel is 5. If I put in 6, my default pressure vessel is 7. So by default, we have 1 spacer at the end.
Yeah. And again, if you're going to run it high, sorry, guys. I was going to say, if you run it.
Continue.
Thank you. I was going to say, if you're always going to run at high recovery, then you don't need to put in that spacer. We'd like to have the flexibility. So for this project, we actually didn't have the spacer, but yeah. So let's just go 5 elements, and then go to the flow calculator.
Okay. So
the recovery was 93% for this project.
93% recovery.
And then because this was a more challenging application, really pushing the limits here, for the concentrate recycle, we went 7.9 cubes per hour, which is 35 GPM. So that's the same as CIP crossflow, which would be really hard to get with traditional. But
yep.
And then the PF cycle, let's max that out as well. So the feed ratio is 110 to 150%. So let's make that 150.
Take it up to 150.
And then the recovery, you can go down to 10 before the guideline flags. Let's go right down to 10%.
Mm-hmm. And what we're doing actually is raising the concentrate flow during the PF cycle. Right.
So the feed ratio increases the flow during PF, so you have more water, so for more cross flow. And then the low recovery just gives you that higher cross flow.
Yeah.
So that's essentially the same. That recovery is the same as traditional.
Mm-hmm.
So that's why we're making less water during PF. So to have it available to flush out the concentrated brine and to have the higher cross flow. Okay, right. Let's look at the report and see if we have any warnings.
So we run it. Okay. And we have only one warning on it, which is for the cycle 1, which is the PF cycle, the last element. We're just a little low on the final concentrate flow, 4.47. Our recommendation is 4.54. So now we go back to the flow calculator, and you can actually see that 4.47 was actually shown here on the flow calculator. So knowing that our limit is 4.54, we don't have to keep running designs to tweak it up. We can just watch this value right here. So as Brent said, we could raise the feed ratio, and it'll update. Now you're outside our recommendation, so you're going to get what we call a warning. So you'll get this little pop-up that you're outside our recommendation, but it will accept your value. And on a challenging water like this, you might have to do that. Just looking at this at 4.75, that's actually a lot higher than I needed. So I don't have to exceed our recommendation by quite that much. Just accept that. I need 1 more %.
Yeah, so the flow calculator, Garth's done an amazing job organizing this. So you can see all the data, like you said, before you actually work out the hydraulics before running the report.
So now we know that our concentrate flow is 4.56 cubic meters, and we saw from the warning that you want to be above 4.54. So we'll be fine there, and we expect we should be fine on everything else.
Yep. So that's 20 GPM for our friends here in the States.
Yep. And we just scroll down to the warning table. And we got rid of warnings tied to a specific element, which are the ones you definitely want to get rid of. The only thing left is this little that our feed ratio is just a little higher than our normal guideline, which is required to keep the crossflow high enough on the last element in the design.
Yeah, and so the one thing to consider there is when you're picking your pump. So if you run at 100 during CC, then you're going to run at 153 during PF. So you just want to make sure there's room on your pump curve. So that's essentially why that guideline is there, just to make sure you're in the same pump range. So while we're here in the report, I just wanted to show the tremendous energy savings with this project. If we could go up to the flow table, just showing the first and last stages, the pressure.
All right, so our feed pressure was 11 bar when we started the CC, and by the end of the CC, we were up to just under 37 bar. On a traditional RO where you were running steady state, you would need enough pumps and permeate throttling to get up to about 37 bar on your last stage, steady state. Here, you're going to ramp from 11 up to 36 and then back down. So you spend very little time actually at the max pressure. So your average pressure is going to be, somewhere between 11 and 36. So 20. So you're going to be averaging maybe closer to 20 over the course of a cycle, as opposed to having to design for 36 continuously.
Yeah, I think the energy savings on this project was just over 30%, so quite significant.
Yep. Okay, so Brett, was there anything else you wanted to illustrate?
Yeah, so that wraps up the cases. The last comment I'll make is, if you take this same design, and maybe we could share this projection, and you try to do the same thing with a traditional design, I can tell you it's just extremely challenging. You're going to get a lot of warning, and you can do it, but you're going to be doing, permeate throttling, interstage booster, concentrate, recycle, this whole balancing act that I mentioned previously.
Yeah, I spent 20 minutes yesterday and was not able to get a design with no warnings.
There you go. Yeah, so we just want to stress how easy it is. It really is just a better mousetrap. But that's it for cases. I guess we can, with the last 15 minutes, we can open it up to questions.
Yeah, maybe you could take this design just back to the design tab, and we could talk through a couple of the audience questions.
Sure.
So if we look at if we go into the flow calculator. When it comes to traditional RO, we typically flush with low flow rates, but in CCRO, it's been noted that we use a fairly high flow rate for the PF. So, Brent, what's the logic for keeping the flow rate high during the PF?
Yeah, so the goal is to get back in CC and just to flush it out, in general, as fast as we can. So the less time you spend in PF, the more time you spend in CC. So if you have more time in CC, it actually brings down the flex rate. And then also just to have the energy just to blast out anything that started to precipitate in the last batch. So in general, we say we like to have the same crossflow during PF and CC, which is the default settings will give you that if your GFD is around 15 or low 20s LMH. But when you have like wastewater reuse or a lot of pressure vessels, then it could be more of a challenge to get the same flush, just because now you have less water and more pressure vessels.
Right. So one of the things, continuing on sort of the theme, is if I change that feed ratio back down to 120, you notice that the length of time you spend doing the flush went up. So if I go back to the default, I'm going to spend, just about 2 minutes, 40 some odd seconds in this flush mode. Kicking the flow rate up, I make this flush much shorter. You can get back to producing water.
Yeah, which is part of the reason why we like, we're a high recovery. We like to run at high recovery, and then we have a different product for lower recovery, which essentially removes this PF step. But we're not going to talk about that today.
All right, thanks. Could you address why we only use 5 elements in this case in a 6-element pressure vessel, and what the advantage is of using 5 elements?
Yeah, so I know over the years, when we started, all the pressure vessels were 6, and then there's 7, and now they're 8. So when Desalitechs started, a lot of our applications were more challenging. So we went with the 5 elements just to get the best flex distribution and cleanability. And then what the spacer does, it increases the volume of the system. So the more volume in the system, the longer the CC duration time. So this isn't an issue at high recovery. Maybe we could demonstrate that.
Sure. If I drop this down to 5 elements, I get rid of the spacer.
Yeah, that helps. And then just keep dropping the recovery by 5 each time. And then you can see the CC duration will dramatically decrease. So right now it's 35 minutes, and we like to be above 5 minutes. So in this case, it's not the best example because it's wastewater reuse, and it's 10
really
GFD,
high,
17 LMH. So we have a lot of volume to begin with.
But I'll take it back down to the default values just to play with the hydraulics.
Sure.
So with the defaults, we had a 23-minute duration. If I add the extra pressure vessel, yep. Okay.
So if you go down to 80%, you'll see that drop significantly.
Yeah.
So it's each cycle is the volume of the system divided by the circulation flow rate. So the more volume, the longer the cycles. And then recovery, the higher the recovery, the more cycles, which is intuitive, right? To concentrate it up more, you need more cycles. So you can see that 80%, we drop to 10-minute duration. So maybe you go down to 75%.
No, this is going to come way down. Yeah.
So now we're at 7.4. So we're still above the 5 minutes is the min. We'd like to be above 10 even. So if you go and add the 6 element for the pressure vessel size, that'll jump maybe close to 10.
Yeah. Didn't change it. Yeah.
So anyway, it's when you have a higher flux, you'll see if you want to run at 70% recovery and you're 15 GFD or low 20s LMH, you absolutely have to have that spacer. So 5 and a 6 or 6 and a 7. So our product line has just been developed around 5 elements in a 6M pressure vessel. So for double pass, the second pass, we quite commonly go 6 elements in a 6M. And then on easy applications, a lot of times we'll go 6 and 6 if you don't want that flexibility. But it's nice to have that flexibility to increase your flow by 20% in the future. And just the flexibility to run with the same unit again at 75% in the morning and then 98% in the afternoon. And that really does happen in wastewater reuse applications, right? Where the feed water changes dramatically.
And as far as feed water quality, there's a few questions about what the feed water quality limits are for CCRO and if and how they differ from a traditional RO.
Yeah, they're the same. So I had highlighted that earlier. So we follow the same guidelines. It's harder to get the warnings and it's easier to get rid of them, which you'll see when you start playing with the CCRO module.
And when it comes to determining your recovery and understanding, the effect of silica saturation or saturation of other sparingly soluble salts, how do you go about determining what the maximum possible recovery is for a particular application and water quality?
Yeah, so we run the anti-scalant projections, rely on the chemical suppliers. The downside of the anti-scalant projections is they don't take into account our induction time advantage. So a good example is we've had success with silica at low pH. So the industry standard is, 300 ppm of silica in your brine is the max, and that's what the anti-scalant projections will show you. But we've run it up to 5, 6, 7, 8, 900 ppm, and we do that at low pH because it increases the induction time, or the time it takes for silica to scale out. So it's this, we concentrate it up and then flush it out essentially before it has time to plug up the membranes. And even if we run for 30 minutes, remember it's only the last few cycles, the last 3-4 minutes that the salts are super saturated. And then you turn around and flush with super clean water, and potentially dissolve some of that scale back into the water. So you concentrate it up, and then it's almost like doing a permeate flush every 20 minutes or a feed flush every 20 minutes. But you're doing that without wasting water.
And can you describe how that the PF or flush is initiated?
Yeah, so the default is a volumetric calculation. So we just monitor the volume, and then when you hit your ratio for 90 or whatever recovery rate, then we trigger the flush. But we also have the flexibility, and we do monitor the connectivity in the loop. So just say, you want to run your system, you have varying feed water, and you want to run your brine up to 5,000 TDS. So regardless of what the feed is, the system will just keep concentrating up to 5,000, and then it'll trigger the dump or the PF mode. Then the other one is pressure, which we don't use as much, is more just as a safety. And then the third one is permeate. So just say you had a permeate target that you need to hit, the strict permeate target. With recovery, obviously higher recovery, the permeate gets worse. So we can push the recovery right up to that permeate target. And then once we know we're going to exceed the permeate quality, then we'll trigger the PF. So the recovery just becomes a function of how long you can run before you hit your target permeate.
Yeah.
All right. Another question that's a bit of a theme here is how to select the appropriate soar element in the CCRO design.
Okay. Okay. Well, we mentioned that we have several different elements, the 3,000 up to the 5,000, then the 6,000, 7,000. The wastewater, which is what we're currently looking at, doesn't recommend the 6,000 or 7,000. So the list gets shortened. But you can look at your water quality and pressure. And if the water quality is better than you needed, so, you can come down, and I have a TDS of, 88. And if that's more than good enough, you could check what would happen if I went down to the 4,000. Because I'll save on, it's a little looser membrane. I'll lower pressure, a little higher TDS. So I went from 88 to 260. But I dropped the pressure way down.
So in most applications, it's going to default to that 5,000. So it's relatively easy, right? You just go up or down based on the permeate quality that you want.
Mm-hmm. And for the sake of argument, if you wanted to show what happens, they don't call it wastewater. I should get the entire list now. Yeah. So I got it a little lower TDS, in this case 86. So depending on the exact feed water and the product requirements, you can move up and down, which will affect the recovery, or the reject ratio, and the pressure requirements will change. But as Brent said, normally start at the 5,000 and then adjust up or down as needs be.
Thanks. I guess the next question we have is if you can show us what version of Wave you're using that includes the CCRO design module.
Okay, the CCRO module was released starting with Wave 181, which has been posted to our website this week. So you would need to update your Wave to the latest version to get the CCRO icon. And then there'll be another update next month. So to get the CCRO, update Wave off our website.
Thanks, Garth. So we're quickly reaching the top of the hour. We have a lot of questions that I know AC has been busy in the background answering as many of these as possible. There's a number that we've yet to answer that we haven't had time to ask during the live webinar. So we will address this list offline. And for those of you in the audience who have asked questions and haven't heard them or haven't had them responded to as yet, we will work at getting you answers to your questions. And in closing, I guess thank you to Brent and Garth for the Wave demonstration, and thank you for attending. I'd like to invite you, the audience, to join a live Blue Talk discussion on February 4th. It's going to be featuring Kimberly Kupiecki, our global leader for sustainability, advocacy, and communications, and Beshrevul Dagmoudi, global water program leader at Kimberly-Clark Corporation. Together, they'll discuss governance, partnerships, and how supplier relationships are changing to solve global sustainability problems, and what's sure to be an interesting dialogue. Hope to see you there. Garth, Brent, do you want to say any final words?
Mm-hmm. Just thank you, everyone, for joining our little webinar this morning. I hope you found it very interesting and learned something from it. Have a good day.
Yep. Thanks, everybody.